Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam.
Waalaikumsalam, sir.
Waalaikumsalam, sir.
Okay, so today we will continue with our lectures. So lecture 3B regarding time response of first order system. So today we will also cover tutorial number 6, okay, related to first order system. Okay, so so let's see what is first order system, what this is about. Okay, so after completing this lecture, students, you guys will be able to understand the concept of poles and zeros, and then determine the time response of a first order system using poles and zeros, and then determine the performance parameters of a first order system. Okay, so firstly, we will look at what are poles and zeros. Okay, so in previous lectures, we have learned about deriving transfer function and what is transfer function, but we don't know what is basically the use of transfer function. So one of the use is to obtain poles and zeros. So for now, we will go into understand about poles and zeros from transfer function, how to obtain this. So let's look at poles. So to find poles, the first rule is the poles is basically the value of Laplace transform variable s. So the value of s that cause the transfer function to become infinity. So the poles is basically the value of s that makes the transfer function becomes infinity. And then the second rule is the poles are any roots or punca, roots of denominator of the transfer function that are common to the roots of numerator. So basically, poles are also the roots of denominator of transfer function or dia punya pembawah, okay? So let's say our transfer function, let's say TS, we have numerator divided by denominator. So poles are the value of denominator or the roots of denominator or the value of s when denominator equals 0. Okay, so let's look at an example. So let's say you are given this transfer function gs equals s plus 3 divided by s plus 5 times s plus 2 times s plus 3. So how to find the poles? So using the first rule, so the first rule states that the poles are the value of s that causes the transfer function becomes infinity. So this function gs will become infinity if the value at the bottom here, denominator, equals 0. So the value of s that causes the denominator become 0. So the value of s that causes denominator become 0 is s equals minus 5 or s equals minus 2 or s equals minus 3. Okay, so the poles of this transfer function are minus 5, minus 2, and minus 3. So there are 3 poles in this transfer function. And using the second rule, so although the term s plus 3 here are the same and we can cancel this out, but the value minus 3 is still the poles, okay? Even though you have cancelled them out, okay? But it's still the poles of the transfer function. Okay, so please remember to find poles. Basically, the value of s when denominator equals 0. Okay. So please remember this because we will use the concept of poles and zeros until the end of this course. Okay. From now until the end of this course. Okay. Next, what are zeros? Okay. So the first rule for zeros is that it is the value of s that causes the transfer function to become 0. Okay. So poles just now is the value of s that makes the transfer function becomes infinity. But for zeros, it is the value of s that makes the transfer function become 0. And for the second rules, it is the roots of numerator, okay? Numerator that are common to denominator. So again, ts equals numerator divided by denominator. So zeros is the value of s when numerator equals 0. Okay. So let's look at an example. Okay, so we use the same transfer function gs as previous. So using the first rule, so to make this transfer function become 0, so the top one or the numerator must become 0. So the only way the numerator becomes 0 is when s equals minus 3. So the 0 of this transfer function is minus 3, only 1 0. So just now there are 3 poles, but for 0 there is only 1 0. And if you use the second rules, even though we can cancel s plus 3, but minus 3 is still the 0 of the transfer function, even though you have cancelled them out. Okay. Okay, so please remember, zeros is where the value of s when the numerator equals 0. Okay, so poles just now is the value of s when the denominator equals 0. Okay, so please remember these two concepts because we are going to use this until the end of this course. Okay. Okay, so let's look at another example. Okay, so let's say you have this transfer function s plus 7 divided by s plus 1 times s plus 1 times s plus 3. So the 0 is minus 7. So the 0 is when the numerator equals 0. So s equals minus 7. And the poles are when the denominator equals 0. So you get minus 1. Again, minus 1 2 times. 2 times minus 1. And then minus 3. So there are 3 poles. Minus 1. Another minus 1. And minus 3. Okay, so if you have, let's say, 3 minus 1 here. Let's say 3s plus 1. So you have 3 poles that equals minus 1. Okay, so you must write all values even though it's they are the same values. Later on we will see why even though they are same value, why we need these 3 poles and we assume they are different. Okay, later in subsequent chapters. And then another example, let's say we have a transfer function gs equals s plus 13 times s plus 3 divided by s plus 11 times s plus 2 times s plus 9. So the zeros are minus 13 and minus 3, and the poles are minus 11, minus 2, and minus 9. Okay, so I hope you understand the concept of poles and zeros. Okay. Now we move on to looking at the time response. Okay. So last time I explained about you have a function of y in terms of time, and then you use Laplace transform, to convert it in terms of frequency. So the function with time is basically the time response. And the function with frequency is frequency response. Okay, so in a control system, both of response are important, and sometimes we need to choose in whether we want to analyze a system in time or in frequency. And in this lecture, we are choosing to analyze the system in time. Okay, so we want to find the time response. So time response of a control system is the time solution of a differential equation. So instead of frequency, we solve the equation and find the solution in terms of time. So usually time response consists of natural response and forced response. So natural response is caused by the system itself, and sometimes it's called the transient response or homogeneous solution. And forced response is caused by the input, and sometimes we call it steady state response or particular solution. So if you still remember about your ODE, kelas ODE, tak tahu dia punya code apa dah. So you probably still remember code, okay? That in ODE, you can solve, let's say, y double prime plus y prime plus y equals 0. So when this equation equals 0, so we call this a homogeneous ODE. But let's say we have the same equation, but not equal 0, maybe in terms of a function. So we call this inhomogeneous. I'm not sure yet, I forgot the real term. So basically it's the same thing explained here, but the explanation is in terms of control system. Okay, so the natural response is the value of y when the ODE equals 0, and the forced response when you have the FT here. Okay, so let's look at a plot, an example plot. So let's say you have a plot of a time response. So usually the beginning part here, before reaching the steady state value, is the solution of the time corresponding to the natural response of the time response, which is caused by the system itself without the effect of input force. And then the steady state response here is caused by the input. So if you have an input, then the input that cause steady state error. Okay, it's not really important here. I mean, there will be no question asking you what is natural response, what is steady state response, but it's worth to understand what the meaning, okay, of natural response and what the meaning of steady state response. Okay, so let's look back at the procedure to obtain time response. So we have learned this basically from lecture number 2 until lecture chapter 2, okay? Laplace transform until gearing, rotational mechanical system. So let's say you have a schematic of a system. So firstly, you draw free body diagram, and then you find the equation of motion. Then from the equation of motion, you can straight away plot the graph or solve the equation of motion. But sometimes you might have an equation or ODE that is difficult to solve in time response. So you use Laplace transform to make it in algebraic form. Then from Laplace transform, you rearrange to get transfer function, and you get a fraction, and you use partial fraction expansion to obtain the time response. So there are two ways of obtaining the time response. You can use the solution of the ODE straight away, or you can use a Laplace transform, find the transfer function, and obtain the solution in terms of time. So if you look at this procedure, you might wonder why we need to use transfer function. It seems like the procedure is longer. So let's look at an example. So let's say you have a system, input Rs equals 1 over S, going through a transfer function Gs equals S plus 2 divided by S plus 5. And you want to find the output Cs. So how to obtain the time response of Cs? So first, we need to find Cs. So what it means here, we need to find Cs in terms of G and R. And then we perform partial fraction expansion. And then we perform inverse Laplace transform. Okay, so let's look at how to find Cs. So Gs here equals output divided by input, and it's equals Cs divided by Rs. So to get Cs, you just rearrange. So Cs equals Gs times Rs. So you can just substitute Gs and Rs. So what is Rs? So Rs here is 1 over S, but can Rs has a different values? So let's look first what is Rs. So basically Rs is input, and there can be many types of input. So the most common inputs are step input, or figure number 1 here. An input that is constant with time. So if you use Laplace transform on RT, you get Rs equals A over S. And RT also can be in terms of ramp input, or it's linearly changed with time. So if you use Laplace transform, Rs equals A over S squared. And sometimes RT can be in terms of trigonometric function. So here we use sine input. So if you use Laplace transform, then Rs equals A over S squared plus omega squared. So there are many types of Rs, but the most common Rs are step input, ramp input, and sine input. So sometimes in exam, maybe the question says, find the transfer function of Cs when, find the time response of C when it is applied to a step input. So you might wonder, what is step input? So you need to understand that step input is just a constant. Ramp input is constant times t, and sine input is constant times sine omega t. So maybe in question they don't give you Rs equals what. They just state the name. Okay, Rs is step input. Okay, for example. But in this case, Rs is called unit step input because the constant A equals 1. So when A equals 1, we call it unit. Okay, unit step input. So let's say if we have unit ramp input, so basically RT just equals T. or unit sine input. So unit sine input equals sine omega t. Okay, so sometimes in exam they just say when RT is unit step input. Okay, so sometimes they say RT is unit step input without giving you the equation of RT. So when so here it's already given RS equals 1 over S. So you just substitute GS and RS. And then here you perform partial fraction expansion. So you find A and B, and then substitute back into CS after you find A and B. And then you use inverse Laplace transform to get the time response CT. Okay, so you have learned this in lecture number 2, 2A again. And then you can plot the graph of CT. So you will get a graph something like this, the purple one here. So the curve part here is transient response, and then the steady state part here is the steady state response. Okay, so let's analyze the transfer function again, and how we can use the concept of zero and pole that we have learned in determining the time response of this system. So here, the transfer function GS, we have poles and zeros. So poles is S equals -5. So the value of denominator equals 0, the value of S when denominator becomes 0. And then we have zeros equals S equals -2. So it is the value of S when numerator becomes 0. So you can plot poles and zeros on a plane called S-plane here. So an S-plane has imaginary axis, y-axis, and real x-axis. So if you plot the input pole, so the input RS here, the pole is S equals 0. Okay. So you can plot on S-plane the input pole at 0 here. So usually we will represent poles as X and a circle for zeros. Okay. And then we can also plot the system 0. So for the system 0, the GS, so we have 0 equals -2. So we can plot -2 on an S-plane. So here it uses a circle to represent 0. And then we can plot the poles. So the poles is -5. So it uses a cross. So if we look at the value of poles from the input zeros and poles from the transfer function, and we look at the output transform, the CS, it basically represents this section of the equation of CS. Okay. And then when this frequency response is converted to time response, so we get the first part here, which is from the input, becomes a constant here that corresponds to the force response. And then the second part here, which is coming from the system or the GS, when converted to time response, you get the natural frequency or the natural response, sorry. So the first portion here represent the force response, and the second portion here represent the natural response. So we know that if we obtain the pole from the input, then we can know the shape or the type of force response. So here, the force response is a constant because the poles is equal 0. And then we have the system pole equals -5. And then the type of response is exponential, okay? So later on, we will see more about how to determine a system response using poles and zeros. So input pole basically generates the force response, and the system poles generates the natural response. And then the system poles, which is -5, generates the natural response in the form of exponential. Okay, so it causes the shape of natural response to have an exponential shape. So both zero and pole actually generates the amplitude of the time response, which is the 3/5 here. Okay, so that's basically what poles and zeros, the purpose of them is actually is. Okay, so I hope you get the idea of the purpose of poles and zeros. Now let's look at some types of control system in terms of the order, okay, order of a control system. So the order of a control system can be determined by looking at the highest order of the differential equations or looking at the number of poles in the transfer function. So for example, if you have y double prime plus y prime plus y. So this ODE is second order because it has double prime here as the highest differential equation. So let's say if you have y prime plus y double prime plus y triple prime. So it's a third order because the highest differential order is 3, okay? So this is how you look at the order of a system. Or sometimes you can look at the number of poles. So let's look at GS that we have previously. So S plus 3 divided by S plus 2, S plus 3, S plus 5. So here, the GS has 3 poles. 1 pole here, here, and here. So when GS has 3 poles, meaning that GS is a third order system. Okay, so you can look at the order of system by looking at the highest power of the differentiation, or looking at the number of poles a transfer function has. Okay. So for now, in this lecture, we look at only on first order system first. Okay. So first order system basically it has y prime only or one pole. So let's say you have a system RS input GS equals A divided by S plus A, and CS is the output. So look at the GS here. So you have A divided by S plus A. So here you have only one pole, which is S equals minus A. So one pole meaning that GS is a first order system. So you can plot the pole on S plane. So S plane again, the y-axis is imaginary value, and the real axis or x-axis is the real value. And let's say you want to find CS or CT, so by inspection. Okay, so ignore the mathematical process. So CT is equals K1, a constant, plus K2 times E power of negative AT. Okay, so you can find K1 and K2 by using partial fraction expansion. So if you have GS equals A divided by S plus A, then CT, the time response, equals 1 minus E power of minus AT. So this is the first formula in this lecture. So for first order system, so if you have GS equals A divided by S plus A, the time response is 1 minus E minus AT. And RS must be unit step input. So when RS is unit step input and GS is first order A divided by S plus A, the time response is CT equals 1 minus E power of negative AT. Okay, so let's look at more detail about this. So if you have the time response, then you can plot the graph of the time response. So there are some constants that you need to find that actually describe the properties of the time response. Okay, so we call that parameters or constants as the performance parameters. So performance parameters of the first order system. So the first performance parameter is we call it time constant. So time constant is defined as 63% from final value. Okay, so somewhere here, or the formula is time constant TC equals 1 over A. Okay, so this is another formula you need to memorize tapi tak keluar exam. Okay. So time constant is 1 over A. So here you will see that to find time constant, you only need the pole, okay? The pole of the transfer function. So you don't need the other things like input and so on. You only need the pole of the transfer function to find the time constant. Meaning that you don't need to solve this to find CT. You just look at the transfer function, find the poles, and you get time constant straight away. Another performance parameters is called rise time. So the rise time is the value of time to rise from 0.1 of the final value until 0.9 of the final values. And some calculation. So the value of time response is this TR equals 2.2 over A. Okay, so it's the same for all first order system. And then lastly is the settling time. So settling time is the value of time to reach 2% of final value. So the formula is TS equals 4 over A. Okay, siapa yang berminat nak tahu macam mana dia derive, boleh tengok Wikipedia ke YouTube. But we don't explain the derivation. We just give you the definition and the formula. Okay. Okay, so we have three things just now. We have time constant, PC equals 1 over A. Rise time equals 2.2 over A. And settling time equals 4 over A. So this is only for first order system, GS. So GS equals A over S plus A. Under unit step input. Okay, so this is the formula for first order system A over S plus A under unit step input. Okay, so let's look at an example. So let's say you have GS equals 50 divided by S plus 50. RS is a unit step input. So first you find the poles. So the poles is A equals minus 50. So by inspection, the solution will be Ct equals 1 minus e power of negative 50t. So the time constant is Tc equals 1 over 50 second. The rise time is 2.2 over 50 second. And settling time is 4 over 50 second. Okay, so you just substitute into the formula given. Okay, senang. Tak pernah subjek ni sesenang ni. Oh, Abida. Okay. So we have completed lecture 3B. Any question before we look at tutorial? Okay, so let's look at some tutorial. Okay, so tutorial 6 about first order system. Okay, so tutorial 6. So question number 1, determine the time response and performance parameters of the following system. Okay, so before we blindly answer the question, let's write the equation involved for first order system. Okay, so first order system. So GS must be A over S plus A under unit step input. Oh, what is this? Okay, so and then we have time constant Tc equals 1 over A. We have rise time equals 2.2 over A. And settling time equals 4 over A. And then the time response Ct equals 1 minus e power of At. Okay, so this is basically these are the only formula for first order system. Okay, so question number 1. So GS is 200 over S plus 5. Sudah. Tak sama. Okay, tak tahu jawab. Okay, see you next week, neighbor. Okay, so when you have this, try to make it equal A divided by S plus A. So you realize that A is 5, okay? But the numerator is 200. So what you can do is factorize to make it 5, okay? So what you can do is you can do 40 times 5 over S plus 5. Okay, so you factorize. And kalau confused juga, tulislah 40 times 5 divided by S plus 5. So now you can see that this portion here is first order system, okay? Similar to the formula you have. So let's find the time response. So CT, if you use this formula, you get 1 minus e power of negative 5t. So how to include 40 here? So just multiply 40 times. Okay, so this is the time response. And how to find the performance parameter? So TC. So TC is 1 over A. So you get 1 over 5. Okay, so time constant, it doesn't affected by 40, okay? Because time constant is only affected by the poles. So you don't need to multiply with 40. It's just dependent on the poles of the first order system. So similar to TR, 2.2 over A. So you get 2.2 over 5. And TS is 4 over A. So equals 4 over 5. So the only thing that need to multiply with 40 is the time response, CT. But all the time constant, all the performance parameters remains the same because it only depends on the poles. Okay. So question B, I hope you can try it by yourself. It's similar to GS. So GS you have 200. So in question A, but question B you have 20. Tak boleh fikir juga, bolehlah consider tukar course. Okay, so let's look at question number 2. So determine the transfer function and performance parameters of the system with time response below. So you are given a graph instead of equation. Okay, so from here you need to go back to the definition. Okay, definition of all the time performance parameters and so on. Okay, sebenarnya saya pun tak tahu macam nak jawab. Let's go back to the lecture notes. Okay. Okay, so firstly, we need to find the value of A. So A, you need to find the initial slope. Jam, macam nak jawab ni? Okay, cek jawapan sekejap. Okay, so firstly, we look at the final value here. So first we need to find the constant A, the poles, okay? So to find the poles, you use the formula for time constant. So it's 63% of final value. The time when it reached 63% of final value. So the final value given from the graph is somewhere about 0.7, 0.71 or 0.72, okay, somewhere about that. So let's jot down final value equals 0.72, okay, somewhere about this. So time constant equals is 63% of final value. So TC equals 63%, which is 0.63 times the final value 0.72. So you can use calculator. So you should get about 0.4536. Okay. So from here, oh, it's not the time constant yet. Okay. So from here, you find 0.4536. So maybe somewhere here. Okay. Okay. So from the graph, so kena look pakai pembaris lah. So saya tak ada pembaris. Korang pandai lah. Okay. So from 0.4536, so TC is somewhere about 0.1, maybe 4 or 0.13 ke. Okay, mana-mana lah. Okay, hampir yang lebih kurang values dia. So let's ikut je jawapan dalam jawapan saya ni 0.13. Okay, but if you get other values, that's fine. Okay, it's just this question just want to test you guna pembaris. And then we go back to the formula for time constant. So time constant equals 1 over A. So equals 0.13. So find A. So A equals 1 divided by 0.13. So you get A about 7.69. This is the poles. Okay, poles of the transfer function. So you get the transfer function GS equals 7.69 divided by S plus 7.69. Tapi tak habis lagi. Because if you look at this transfer function and the original graph, it is when the steady state value equals 1. Okay. But here the steady state value is 0.72. So again, what you need to do here, you need to multiply the top here with 0.72. Okay. Sebab dia dah just scale down. Okay. So you get about 5.54 over S plus 7.69. So this is the final, the transfer function of the system. Okay, so it is scaled down. So if you don't multiply, you assume that the steady state value is equals 1. But now the steady state value is 0.72. So you must multiply with 0.72 on GS. Okay. So the time response, CT, equals 0.72 times 1 minus E power of 7.69 T. Okay. So similar to question number 1 just now. So you have a scale. Okay. Then from the value of A, you can find TR. So TR is just 2.2 over A. So 2.2 over 7.69. And TS equals 4 over A. So over A. So 4 over 7.69. Okay, so that's it for this question. Okay, any question before we end this lecture?
No, sir.
So far faham, sir.
Okay, bagus. Okay, so now you can try project part 2. Okay, so project part 2 is related to first order system. Ada tak kalam? So you can try part 2. Mana part 2? Project description. So part 2 is about first order system. So I hope you can try this project part 2 and also the MATLAB part. Okay. So simple je. You need to manually calculate TR, TS, TC, calculate CT. So you have formula given already. So you don't need to derive, okay? And then sketch. Sketch ni pandai-pandai lukis tangan ke, pandai-pandai lah. Okay, find the poles, sketch in S-plane. And then you validate your calculation with MATLAB, okay? So you do in MATLAB, validate your sketch, sama tak sketch awak tu dengan MATLAB, and then validate your calculation, whether your calculation is similar with the one obtained in MATLAB. And you can follow this link here. So in the link, it already give how to write sikit je code dia in MATLAB. Okay, so please do it now lah sebab dah week 5. So ada 2 minggu lagi. Week 6. Week 6 dah. Week 5. Entah week berapa tak ingat. Okay, so we have covered part 2 for the project. So we only left with part 3. So part 3 will be about second order system, which we will learn next week. Okay. So I hope you understand. If you don't understand anything related to the lectures or question, please let me know. And that's it for today's class. And see you again next Monday, insyaAllah. Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
Salam,
Thank you,
Doctor.
sir.